we had a look at the numerical solution strategy. And we've seen that using the concept of a value function, the numerical optimization, or the optimization problem can be reformulated in a very elegant way by distinguishing between two effects, the effects of the control on the immediate utility, on the instantaneous utility, which depends on the control itself in general, and the state variable, might also depend on time. So that would be this U, that's the immediate effect, and we have to trade off this immediate effect with what's going to happen in the future, so the rest of your life. And this can be summarized by the value function as of tomorrow. Of course, it has to be evaluated at the state of tomorrow, and this tomorrow's state depends again on the current state, which we can't influence because it's just given, and the current control. And these two values deterministically determine what's going to happen in the next period. Of course, this is not realistic, but we are going to relax that only later. So we always have to trade off these two effects, and that's quite complex because we do not know tomorrow's value function in general. There's only one period where we do know tomorrow's value function, and that's the final period, because in the final period, there is no tomorrow. And therefore, the value function only consists of the immediate reward, of the instantaneous utility. So in the final period, it's relatively easy in general to solve this optimization problem. Then we've got the value function for the final period. Note it's a function, so we have to know this value for any state, any potential state. And once we know this value function for the final period, we can use the equation above, this one here, to solve for the value function in the last but one period, capital T minus 1. And then we just go backwards in time. Right, this is what we did. So this is the backward induction. And we've seen that for a very simple example where we had to find the best path through some states. Okay, just a couple of remarks. At first sight, if you compare the dynamic programming approach to the Lagrange approach, they look quite similar. And of course, the optimization, the first order conditions are very well, they are the same essentially because it's the same optimization problem that we solve. But from a computational perspective, this backward algorithm for the dynamic programming approach is more elegant, or it actually makes the computational approach feasible. While on the other hand, solving a potentially very large system of nonlinear equations, which we would have to do in the Lagrange approach, is much more demanding. So this splitting up or reformulating the optimization problem in such a way that we only have to trade off today and the rest, or the continuation value, that's another term that we haven't used so far, I think, makes the numerical solution much easier to do. All right, so this is what we did last time. If there are any questions, this would be a nice opportunity to ask them. Okay, if not, then we go over to the first numerical exercise. But before we actually start with the exercise, I'd like to give a very brief introduction to how to use linear interpolation in R, and also how to stack functions in R. These are really technical issues, but we need them for solving the exercise. So as you might have noticed, there is actually a second set of slides, which is labeled Tools and Techniques. And this is for implementing things in R. All right, so the first point we need to think about is how can we represent a function in a computer? Because when we solve the dynamic programming problem, then we have to know tomorrow's value function. And knowing a function is not trivial, because knowing a function is something different than knowing a number or knowing a couple of numbers. Knowing a function means that you have to know the value of the function for any argument you input in that function. So how can we represent a function in a computer? And of course, there are many different ways, and some of them I'd like to talk about. Actually, only one I'd like to talk about now, and that's the linear interpolation. But there are other approaches like spline interpolation, which we will also use in this course. Or it might be the case that you do know the functional form of the function apart from number of coefficients. Then that's a very good way to represent a function in a computer. You could use basis functions. That's a quite neat approach as well. Then, of course, neural networks. We are going to do that in the last big part of this course when we talk about reinforcement learning and other approaches as well. For instance, tiling, we won't do that. Little warning, it's not the case that any kind of function can be represented in a satisfying way in a computer. So all these approximation methods, and what we are going to do are approximation methods, all these approximation methods are only approximations. And the approximation can be better or worse. And it could very well happen that there's a certain function which we cannot approximate in a satisfying way. So what we will assume, and actually it's a reasonable assumption usually, is that the functions we would like to approximate, and these functions are the value functions, have a certain kind of smoothness. So they don't oscillate in a wild way in the state space. Okay, so the value function is assumed to be smooth, and then it's relatively easy to approximate it. There are some more representation techniques for functions, but we skip that. So let's start with the simplest case, I think, the linear interpolation. So our aim is to approximate a function f of x in the interval from a to b. That's of course the first restriction. We only represent the function, the value function, in a certain interval. This could be a problem because when we start in the current period 0, we might not really have a clue where the state could be in the final period and which interval we should cover in the final period. Okay? So in that case, this could be a restriction. But let's assume for the moment that we do know the interval that we should where we should approximate the function f of x. Then what we do for linear interpolation is quite simple. We set up a grid starting from x1 up to xn, from the left side to the right side of the interval. Often this grid will be equidistant, but that's not really necessary. Then we compute the function at each grid point. Let's call them fi. So fi is the functional value at position xi for any I. And now it's easy to approximate the function by linear interpolation. We simply assume that between the points, the function is a linear function. So it would be piecewise linear. And of course, then we have kinks. We might not like that. In that case, we need a different approximation method. But if we don't really care about the kinks, then linear interpolation is quite a good approach. So between the grid points, we approximate the function by simply assuming a linear, a line, straight line. Okay, how can we do that in R? Because linear interpolation is very easy conceptually, but it's the syntax in R is a bit strange sometimes. So you have to get used to that. And this is why I'd like to show you how to linearly interpolate functions in R. There are actually two commands for linear interpolation. The first one is approx, and the second one is approx fun, where fun does not really mean fun, but function. And the first command has 3 main arguments. There are a number of optional arguments which are left out here. The first argument is the grid. So X is a vector of grid points, equidistant or not, that doesn't really matter here. So this is a vector of grid points. Then the second argument is a vector of the same length, which comprises of the functional values at the grid points. So this would be F1 up to Fn in this case. And the Approx command has a third argument, which could be either a number or a vector. And in both cases, this is the points where you want to evaluate the function. So the points that you would like to linearly interpolate. So it's either a vector or just a single point where the function is to be interpolated. And then the Approx command returns a list. The list object in R can be, well, visualized as some kind of basket where different things are in. And these things could be anything. So a list could include, say, a string and a vector and a matrix or whatever. And this, the output of the Approx command, is a list containing two things. The first one is the vector of x's again. So this is really redundant. And the second component is the y. The y component contains the linear interpolations. That's what we are after. So that's the Approx command. The Approx fun command is very similar. The Approx fun command has the same first arguments. So the grid points x, the vector of grid points x, and the vector of functional values y. But in contrast to Approx fun does not return a list, but a function, which is actually very convenient. So I think in general, Approx fun is the command of your choice. So I think in general, this one is easier to use than that one, but that might depend on your taste. Okay, so the Approx fun command returns a function. So you could assign the Approx fun to a certain name, and then this name is the linearly interpolated function. We will see that in a second. Okay, so let's assume we have an approximation of a function f, where the grid points are here at 1. This is probably at 3, at 4. Then the fourth point is at 8. And the final fifth point is at 10. We know the functional values. The functional value here is, well, 2. Here it's 6. Here it's 4. Here it's, I don't know, 9. And here it's 5. And we would like to interpolate this function at the point 6.5 here. So what's our approximation of the function f at point 6.5? Well, the two approaches are Approx and Approx fun. And this is how we use them. First, we need the vector of grid points. Let's call it x. So this x here is the vector of grid points. x1 is the first element, x2 is the second element, and so on. So x is a vector of length 5, and f is the functional values at these points. So again, it's a vector of length 5. These are the first two arguments. If we use the Approx command, then we input the first two arguments x and f. And the third argument is the point or points where we would like to evaluate the function. Here we only want to evaluate one point, 6.5. So we just put this argument to 6.5. What we get is a list with two components, x and y. And we want the y component. So you can take out the components of this basket by using the dollar operator. So in this case, this means the function returns a list. We take out the y component, which is just the linear interpolation. So this command here, including the $y, would return the functional value at point 6.5. I forgot to really compute that, but this is what we would get. If we used the Approx fun command, then it's actually simpler. In that case, we would use the command in this way. So we would use Approx fun, vector of grid points, a vector of functional values at that point, and the output would be assigned, say, to an object g. then G is the linear interpolated approximation of the function f. And it's actually a function, and it could be used like a function. So if I would like to evaluate this function G at point 6.5, I would simply say G at 6.5 or G of 6.5. And then I would get the functional value at 6.5. I could also use a grid or a vector of points where I would like to evaluate the function G. And in that case, I would get as a return a vector of functional values at the linear interpolated points. Okay. So this would be the linear interpolation in R. The great advantage of linear interpolation is that it's very fast. So time will actually be a limiting factor in many of these optimization problems. So we have to have fast methods, and linear interpolation is very fast. And it's also implemented in R in a way which returns the linear interpolations very quickly.
May I ask something?
Sure, sure.
I think this is a thing that always puzzles me a little bit, or I always wonder how that works. Suppose could you go back one slide, please? Suppose I have this G object, right? This function. So what I basically can do is I can use this just as a regular function, right? So I could also assume let's find the optimum or the maximum of this G object. So I could just directly apply the command, for example, the optimize command on this G thing, right?
Right. It's just a regular function. It's been defined by you, but you can use this function G as any other function in R. Does that answer the question?
Yeah, that's good. Thanks.
Okay. Any other questions?
I have a technical question.
Uh-huh.
The parameters I get, except for the y, is it possible to input their only numbers? For instance, if you look at the graph, I think x1 was 1 and f1 was 2. Mm-hmm. So do you have to can you put in 2, or do you have to put in 2 times x, like a function?
I think I didn't really understand the question.
So f1 is obviously the function 2x, because yes, if you put in x, which is 1, you get 2. Do you have to somehow put this function into the approx function R command, or do you just have to put in 2 as the y?
You just have to, well, you can only input the vector of functional values. So in this case, x would be a vector of functional values. I think I'd better switch over to my iPad and try to show that here.
I think you are asking I think he says, if I perceive your question correctly, you asked 2 different things. I think. Suppose you have 2 lists of numbers and call them x and y.
Yeah.
You do not know how they are interrelated. They are just they are just generated from somewhere. Then you could use the approx fun command, I think, to get a functional approximation of the basically underlying functional form, which you do not know, right? But the other thing could also be that you know the functional form and you generate basically, or you have a clue about the functional form and then generate the numbers that you are after.
I think my question was a little bit easier, more technical. Do I need to input numbers as y? Is that enough, or do I need to input functions?
No, you don't know the functions. You need to input the numbers. So
okay. Yeah.
Let's assume that your grid points where you can evaluate the function are here. Then you have a vector. Say this is 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 or something. Mm-hmm. Then x would be a vector 1, 3, 6, 10, 12. And you would evaluate the function only at these points, or you would somehow find the functional values at these points. Let's assume they are here and here and here and here and here. Then this would be the vector f containing the values. Say this is 5.
All right. Okay. Yeah.
7 and 3 and 4 something. Then this would be 5, 6, 7, 3, and 4.
All right. Perfect. That answers my question. Yeah.
And then you could say, well, my function g is approx fun of x and f. And then g is actually a function object in R. So in that case, you could say, well, what is g of 7? And you would get some number.
All right. Yeah.
You
Thank
could
you.
also say, what is g at the points 1, 2, 3? And you would get 3 numbers.
All right. Very nice. Cool.
Or a sequence starting from 1 up to 13, step length 0.1. Yeah, and then you would get an entire vector for these grid points here.
All right. Thank you.
A problem of linear interpolation, but that's not only a problem of linear interpolation, but of any kind of approximation, is that extrapolation does not work in general. So if I would like to know an approximation of this function f at point 20, how would I do that? Okay, that's at least it's not obvious what to do in that case. And even at point 11, extrapolation in general is a problem, not only for linear interpolation, but for any kind of approximation. The commands in R just return NA, not available or missing if they are evaluated outside the interval. But you can specify other returns. And sometimes you have to specify other returns because it's the inherent nature of at least stochastic dynamic optimization that you have to evaluate the value function outside the interval from time to time. And there's nothing you can do about that. That only will become a problem later on. So at the moment, this is not really severe, but please remember that extrapolation is something you should put some thoughts in. All right, so there's an exercise. Let's skip that for a second. Let's postpone that for a second, and let's talk about one other technical issue. If we work in finite time, and so far we've only talked about finite time problems, then the value functions are different for each period. So we have the value function for the last period, for the last but one period, and so on. So in effect, we have capital T different value functions, and we have to somehow organize them in R. So what we need is a vector of functions. And in R, it's quite convenient because it's possible to stack the functions into a vector. So it's possible to create a vector of functions, not a vector of numbers. We do that in the following way. We create an that's a rather idiosyncratic command. It's this command which creates an empty vector of length n. And then you can fill the different elements of this vector by whatever you like, functions, for instance. And you have to note that formally this vector is a list. And therefore, if you want to assign something to a certain position of this list, you need the double bracket indexing. So using this notation here, you can assign something into the ith element of this vector. For instance, if you want to put a function in there, you can use this Approx command, and you can write this function into position 1 of the value function. And then position 1 of this vector capital V is a function. It's this function here. And therefore, you can evaluate that, for instance, at point X by simply writing this. Okay, so this will evaluate the function at point X. Right, and there's also a function. So there are two functions which are just about simple technical issues in R. I think it's very quick to do them. The first one is the linear interpolation. The second one is these vectors of functions. Once you've done that, or if you're already familiar with this stuff in R, then you can go on to the other function, to the other exercise, which is I closed that, which is the non-stochastic income stream. And that's an exercise which looks very easy, but which is quite complex. So I think you need some time to solve that, and we'll see how much time each of our breakout sessions need to do that.
Before we go to that, we should talk about optimizing, shouldn't we?
Oh, I forgot that. Sorry. Yes, thanks, Andreas. And we should talk about optimizing. Right, optimizing. Of course, we have to solve the max operator. The value function is defined by solving the max operator. So for the exercise we would like to work on first, what we need is univariate optimization. So let's quickly talk about the optimize command. The command in R is optimize, either with an S or optimize with a Z. And the main arguments this command needs are the following. First one is the function that you would like to optimize. And this needs really to be a function object. The second one is the interval over which you would like to optimize as a vector with lower bound and upper bound. And the third main argument is that you have to tell the function that you would like to maximize rather than minimize. So in that case, you have to set the option maximize is true. Then this command optimizes the function and returns a list with two main components. The first component is the position of the optimum, so the optimal control. And the second argument is the second component of this return object is objective, and that's the value at the optimum. That's the optimal value that you can attain by choosing the control variable in an optimal way. How does it work? Well, the algorithm is a very robust algorithm, and it's actually certain to return the correct result if you have a unimodal function. So if there's one single maximum, you will certainly find that, no matter whether it's an internal one or whether the maximum is attained at the boundaries, at one of the boundaries. So if it's a unimodal function, you will certainly find the optimum. How does it work? Well, it starts by evaluating the function at the left and right boundary of the interval, so at A and B, and at a point which is not exactly in the middle, but which is just the golden section. So it's a certain fraction of the interval, and you evaluate the function here as well. Then you have these 3 points. The next step is that you also take the golden section of the larger of these two intervals, subintervals. The larger one is from here to here. You take a golden section, which turns out to be about here. And now you can say something about where the maximum could be. It can't be in this interval here, because you already know that you have a larger value than these two values here. Okay, so you can already say that the optimum must be in this subinterval from here to B. Okay, you can rule out the first part. So this is grayed out. Then you have essentially the same problem again. You have a lower boundary, a new one, an upper boundary, a small subinterval, and a large subinterval. You take the large subinterval and put in another subinterval in here. And then again, you can say something about where the optimum might lie. It can't be here because this point is already larger than these 2 points. Therefore, we can rule out the right-hand side subinterval. And then again, we have a subinterval with small part and large part. You cut something off the large part. Oops. And you can say something about the optimum again. It can't be here on the left because this point is probably larger than that one. And then you go on and on. And once you don't move any further, so there's a tolerance level which you can set, then you have found the optimum. So even if the optimum is at a boundary, this algorithm is sure to find that. It might return a local maximum if the function is not unimodal, but has many local maxima. That's of course a problem, but there's nothing you can do about that. So any kind of numerical maximization method will return only local maxima, and you cannot really be sure that it's the global optimum. Sometimes the function that you would like to maximize, we call that the maximand, will have some additional arguments. And these additional arguments can be put into the optimize command. But I think it's better to talk about that once we reach that problem. Okay. Simple example. Suppose you would like to maximize this function here, q times s minus p squared, where s is the variable you would like to, that's the control variable. It's a bad notation here because we used to call our control variable c. So here it's s. And p and q are just some additional arguments. You would like to maximize that with respect to s, given p and q. And this is what you do. You use the optimize command. The first argument is the function that, the first function argument is the function you would like to optimize. The second argument is the interval over which to maximize, in this case from -5 to +5. Then you can put in here the values of the other arguments. So suppose p is set to 1 and q is set to 2. And you have to say that you would like to find the maximum rather than the minimum. Then optimizes this function numerically using this golden section search algorithm, writes the output into the object h, and the object h is a list. One component is the maximum component. So by print the maximum, what you get is the position where the maximum is attained. And the value of the maximum is h objective. So this is the highest value you can get by choosing s optimally given p and q, or given p is equal to 1 and q is equal to 2. All right, and there's another exercise. So we have 3 purely technical exercises, and once you've done that, then you can go on and solve the real exercise, the non-stochastic income.